So now going back to our course, which is engineering physics. There's our engineering physics. I posted, did I post it there? Isaac, where did I post it? I posted it in Getting Started, didn't I? It's actually physically in the syllabus. If you dig in there, it's actually physically in there. But I also posted it under the Start Here, right there. Okay? So if you haven't already logged in, you know, that's where the course key is. Now, we're still in the process of trying to figure out to make sure you don't get double billed. That's one thing, and I'll show you how to take care of that because I now have the instructions for that. And I know we're having issues with when you open up your Cengage, not seeing all of your Cengage stuff all together. And I know you're having trouble not seeing the multiple textbooks that I've allowed for this class. So I'm still working on 2 parts to that, okay? Still working on 2 parts to that, but we're getting there. And then I'm hoping, and if you're in my Intro to Engineering class, the Panda Planners are in the bookstore. Now, they don't have a whole number of Panda Planners because I know some of you are Amazon members and it's cheaper for you to get through Amazon. But if you are a sports player, have a book scholarship, those kind of things, then it's worth getting it through the bookstore even at the market, okay? But if you're the other way, go through Amazon and get it the other way. But they are, and I understand they're on both campuses. So I understand they're on both the Enid and Tonkawa campuses. So that part's there. Just to make sure we were all keeping track. Week 1, I did post, I got the lecture posted this morning. Yay! So it's up there. You also have videos and supplemental materials. Yay! We got that in there. And I will continue to add to these items. And one of them, there will be assignment in Blackboard. Probably will hit there tomorrow, but I'm going to show it to you. But it will not be due until Tuesday or Wednesday. It won't be due until Wednesday. That way both classes will have a chance to physically see the stuff that's going to be required for the assignment. So that way we've got it there. All right, so I think we're squared away there. WebAssign, you can link through there. We're getting there. Now, so I'm going to go back to teacher camera so we can do that. 2 other, okay. Are you guys seeing me over there in Enid? I see you guys. Teacher camera? No. Present. Okay. Okay.
Nope.
I'm going to do this. We'll see if this works. All right, there's the document camera.
We're seeing that.
Okay, there's me.
Now we're on teacher cam.
All right, now we're on. I just keep pushing buttons until we get it straight. Keep pushing buttons until we get it straight. I got to go over it because we figured out if I do the light on, unless we do the light on and then we play with the dimmer switch on this, right? And we do, let it adjust for a second. We'll see if that works while we're talking. All right, Sunday night. Okay, Sunday night, we have a super full blood moon. What that means is a super moon means that the moon is closest to the Earth. That's the first thing. So that's why we have a super full moon, because it's close to, which means the moon is going to appear larger than it normally does. If memory serves, but you can find it on a variety of places, okay? You can find the timing and everything on a variety of places, but it will start, we have a total lunar eclipse that's best observed in North America. And it will be the last time we get a full lunar eclipse for quite some time. So it's the last one, and we're going to get probably best viewing. It's supposed to go to totality at about 11:30 p.m. And at totality, it should be a really pretty bright red, because even though it's in the Earth's shadow, it won't go completely black. So it's a super full total eclipse on Sunday night. So if we have clear weather, that'll be great. If we have yucky weather like what we have right now, it'll be a bummer, because it's going to be totally really cool. So that's what's happening this weekend on that one. All right, here's the assignment that will get posted, and we'll actually talk about it. I have a jar. Actually, I don't have a jar. I have an Erlenmeyer flask. It is a standard 500 milliliter Erlenmeyer flask. I will bring it over to you guys in Enid on Friday so you guys can actually see it on Friday. It is filled with standard gumdrops. Your typical standard gumdrop. This is an estimating assignment, not just how many beats per minute that does your heart, how many beats in an average day does your heart beat. This is an actual physical, this is, practical information, because how many of us have seen count the number of Skittles in a jar and you win the jar of Skittles? How many Tootsie Pops, or what is it, at the fair, they usually fill up the back of a pickup truck, right? They do something in the back of the pickup truck. So this is an actual relatively useful estimating assignment. So I have, and my gumdrops are filled to the 500 milliliter mark in my standard Erlenmeyer flask. I want you to estimate how many gumdrops are in the flask. Now, for Tonkawa students, you can look at it, you can take pictures of it, you can do whatever, you just can't pick up the Erlenmeyer flask. When I get over to Enid, I will bring it with you guys so that you guys will be able to physically see it, just like the guys over here in Tonkawa have it. But it's your standard 500 milliliter Erlenmeyer flask with a standard gumdrops in there. And your estimate will be due Wednesday. And I also want included with that estimate how you came up with it. All right, so if you've done a calculation, I want to see the calculation. Okay. All right. And I will tell you somebody got it last time through. So we do the estimate for that. All right, everybody got a handle on the assignment? You guys okay over in Enid? I'll bring it with me so you guys will physically see it on Friday. Okay, let's try this. I'm going to get the light so that we don't have too bad of a glare. See if that helps. This gives us a bright dot.
I think the glare is from the light next to the camera.
Ah, okay. If I turn that off.
Now we're right.
Now we're good. Because if I do a mark on here now.
Maybe turn the light back on. Yeah.
Actually, maybe if I adjust this back.
But is that what adjusts the light on the top?
No, it will actually adjust. Because in my other room, I get. And we played with this on Monday, and it worked a little better. But this one has a delay to it. We'll give it a second. Okay, for those of you that are in calc and have Cengage through your calc book, and your calc book is direct build. Okay, calc book is direct build. It's not unlimited access was what I've gotten you. I've gotten you total inclusive access. Somewhere in your, oh, you're not seeing it over there. You guys have to tell me. Okay, you should be seeing it now. Somewhere in your student email, you should have gotten an email from the bookstore. And it says, welcome to Inclusive Access. So that's the title that you would have seen. And basically, it tells you in here how to opt out. Okay, it tells you how to opt out. But basically where you do, you can go to the nocbookstore.com, select the term and course, and it will say, the text says inclusive access material. And if you want to go for your calc book, you want to opt out. Because through this class and your intro to engineering, you only got billed once. If you're in both classes, you only got billed once. That's why your packet had 2 classes numbers and that kind of stuff. But your account will be billed for the unlimited access. Okay? So somewhere in your email you should have gotten this. I know there was a glitch in the system that say you enrolled after Wednesday of last week, you probably didn't get the email, it didn't get generated, but they're trying to get that back. But this is exactly how you're going to opt out of your calc being charged for your calc book. So we got that part squared away. Okay. Next thing. See if this comes back up. Give it a chance. Keep playing with it. That's getting a little better. See if that works. And we'll play with the light. See if that works. Yeah. Oh, it's adjusting. Give it a second. Now I can't see it at all, right? So let me go this way. There we go. And then part of it is, there we go. That's a little better. Now we'll see what we can do. Now we'll see what happens. It's an experiment. Weirdness. I wonder, just for bringing you. It's working great in my other classes. It's just this room. And it could be the lighting outside today. No, we went this way. Did it get better or worse? Ooh, that's better. Give it a second. All right, we gotta go that way. All right, that looks like it's good as it's going to get. It's looking great for you guys over in Enid, not so much for the guys in here. We'll go with it. All right. You guys, what I have failed to tell you the last 2 days is that we are participating in a pilot program. And that pilot program is related to your WebAssign user interface. So you may see a difference between your calc class and your physics class because we're all part of a beta test. And that beta test actually usually works out for my students that are participating in the beta tests because they're trying to improve the user experience for you guys as students to actually go in and have a better experience in WebAssign. WebAssign has been kind of clunky, kind of awkward, and they're actually doing it to help us out. Now, as I understand it, periodically through the semester, you'll get some questions, potentially some surveys. They may want you for a focus group, and if they have you for a focus group, they usually offer like an Amazon gift card. So we usually get a lot of really cool benefits if we are participating in a beta test. So all my physics classes are in the beta test. They really want to see you guys and hear stuff from you guys because you guys are both in 2 WebAssign classes. You're in a traditional WebAssign class in calc, and you're in the web assigned class and my engineering physics class. So you get to see the differences between the two. What I know for sure, so this is my email that I got for the pilot that we've got. So you're on the student unit, your user interface, and so far, our biggest problem with Cengage is getting everything into the same account so that you can access all your stuff, which is not doing with what these guys are having an issue with. If you decide you don't like what you're seeing in your WebAssign for the physics side, you can switch back between the new user interface and the other one. You can opt out. And then you've got more ebook support for about this class in your ebooks. And then you should have an updated logo between the two. I haven't figured that part out yet because we just looked at Chase's to see if we could see any difference, and nothing jumped out at me. Nothing jumped out at me. And then they're periodically notifying me of any bugs. But I wanted you to be aware that we are using an interface, a new interface, and that we're part of a pilot. All right, so here we go. Now that we got through more, and it's Wednesday. And now, after this class, I think, other than trying to resolve some book issues, at least I don't have any more bookstore issues. I don't have any more bookstore issues, but I have this stuff. So let's see. We stopped on Monday with dealing with our trig stuff, right? We had written. Did I do the trig opposite hypotenuse? Okay, I'm getting shaking of heads. So I didn't do that. So where did I stop? We talked about the number 27? We talked about number 27. All right, talked about number 27. Okay, so let me switch views so I can see what I got. Okay, so we did 27. All right, so here in your book, this is table 1.3. So I talked about the number 27 being roughly 60 miles an hour, right? In your book, you've got table 1.3 that gives you some more familiar numbers to help you on the scale of things. So that when you're actually, because one of the ways that you know, there's some things that you can do to know whether or not your physics problem is correct. And one is this answer reasonable? Which is why we were talking about, if you could draw a 3-inch line. If you know that the 27 meters per second is roughly 60 miles an hour. Those kinds of pieces are going to help you be able to evaluate whether or not your answer to your physics problem is correct. Because most of the time, unless somebody asks a question and I am just plucking numbers out of the air for the sake of doing the problem at that instant, I am going to give you, and I will actually look up reasonable values. So if I tell you that the car accelerates from 0 to 60 miles per hour in 4.5 seconds, that is an actual reasonable number if I'm a drag racer. Okay? So I now ask the question, because it's going to help me out. How many in here are what you might refer to as a gearhead? I got a couple of you. How about over in Enid? Are you guys gearheads? No. Okay. Because I use car numbers a lot because they're easy to look up. And I have access to Car and Driver and Road and Track. Okay? Since I have access to Car and Driver and Road and Track, I like it. They have some really cool tables. It's lots of fun, lots of data. So I like those. So I use car examples. I also am an avid football person, so I use lots of football examples. Both kinds. I use both football and football, right? So I do both kinds. And I will also sometimes use Australian rules or rugby because they're fun and cool. I use lots of baseball examples. I use basketball examples. ski jumping, sports. I use a lot of sports because it's easy for most of us to understand. So I do a bunch of them. And when we get to things like pressure, I use a lot of other pieces that help us out. So that, and because of that, I tend to make sure I have something that's actual practical numbers. And those numbers are realistic. So if I have a horse running 60 miles an hour for 4 hours, it's likely not going to be the answer to the problem unless I'm just pulling numbers out of the air just for the sake of that instant. If I've done my homework and I know the author of your textbook has done her homework, that we will give you reasonable actual values that make sense. So you can actually go in and say, okay, does this number make physical sense? And that's one way to know whether or not you are on the right track with your problem. So that's something so that's why this table is going to be really, really handy in your book. And it's table 1.3 with some common units. It also gives you some common approximate values that if you're using things for estimations, you may want to kind of look at that. So that will help us keep looking at different estimations. So that's one way to know whether or not we're doing things correctly. The other way to know whether or not I'm going the wrong way. The other way to know if we're doing things correctly is something called unit analysis. Okay, so now nobody can see anything. Okay, there we go. And it's gone the other way. There we go. Now I've gone too far. Experimenting. Life is good. A mushroom cloud, I like it. We're going to give it a second. I'm going to turn the lights off now to try it, right? We got it. So it's picking up. See? That's not too bad. That's better than where we were.
Do you have a way to change the color of that to white? Would that help any?
Oh no, white makes it worse. Yeah. And go that way. Now that I know which way to go.
Maybe this room needs blackout curtains.
Something. Give it a second because I know this thing responds slow. That's not too bad. Okay, you guys seeing it okay over there? And Enid? All right. Now we deal with different kinds of optics, different kinds of things. It's always so much fun. Okay, so it's unit analysis. So historically, I'll give you a problem, and 9 times out of 10, what will happen is somebody will go in, well, I haven't seen that before. That's not the point of this problem, okay? It's not the point of the problem, at least at this part in the chapter. So you'll be given an equation that looks something like this. 1/2 mv squared is equal to 1/2 mv naught squared plus the square root of mgh. Okay, so that's what you'll be given. Is that 1/2 mv squared is equal to 1/2 mv naught squared, the square root of mgh. And you're asked to say whether or not this equation is correct. At this point, you don't have to worry any about what these units are for and what this is for. This is all basically unit analysis. M is going to stand for mass, so it's going to have units of kilograms. G is my acceleration due to gravity, so it's going to have units of acceleration, which is meters per second, which is going to be meters per second squared. I'm going to shift it up, meters per second squared. H is a unit of length, so it's in meters. And V is a unit of velocity, so it's in meters per second. Okay, it's in meters per second. What we're doing in unit analysis is my things that add together have to have the same units. So I have to be in the same units on both sides of this equation in order for this equation to be correct. And so what you're doing in the homework assignment is you're trying to make sure that the unit analysis is correct. So if I do 1/2 mv squared and this is 1/2 mv naught squared, we're pretty sure that the units for both of those are the same. This naught right here means initial. Okay, so I can use v sub I for initial. I can use v sub 0 for initial. I can use, and we label our units a lot in physics, so that labeling helps us keep track. So we're pretty sure that 1/2 mv squared on one side of the equation looks pretty right, and we're sure that 1/2 mv squared on the other side of the equation looks pretty right. So the questionable term that we're worried about is this right here. The square root of mgh. Now remember, if I'm in math class, mgh to the 1/2 power is the same as the square root of mgh. I haven't done anything different if I'm using my 1/2 power. I'm just dealing with that representation. Okay, I'm just dealing with that representation. But let's look at the units here. So I've got mass is in kilograms. G is in meters per second squared. And H is in meters. And all of that is to the 1/2 power. Well, if I consolidate my units, I get kilograms, meters squared, second squared to the 1/2 power, which gives me meters per second, and I get kilograms to the 1/2 power. Well, if I'm doing mv squared, right? mv squared, that's kilograms, meters squared, seconds squared. These two things are not equal, so I probably have done something wrong. So when I'm working with my equations and I'm working my problems and I'm working things, your unit analysis is going to save your butts. Because if my units aren't working out, I've done something wrong along the way. And it also helps you find where your errors are. It's going to help you find those errors over and over and over again. So think about in chemistry, some of you have had me for chemistry. I griped about unit analysis all the time because unit analysis was going to help you out. And in chemistry, it's all about conversions. Almost everything is it's just a big, huge bunch of conversion problems. You get it's where's the electron and a bunch of conversions. We don't have a whole lot of difference out there. So that's what we've got going on. And so unit analysis really, really is going to help us out. And so let's do a unit analysis type problem because we talked about conversions. It's lots of fun. So I'm going to do one. Okay, we'll do one, and it's a fun one. I got a turtle here. I got my little turtle. And y'all, just remember, I'm a physicist, not an artiste. Okay. So these are, so my artwork is always entertaining. So I've got a turtle, and my turtle happens to be running along here at 594 furlongs per fortnight. I got a chuckle out of somebody.
We're not seeing what you're writing.
Not seeing? How's that?
There you go.
Yeah.
There you go.
Furlongs per fortnight. Okay. And we all know that that's not that's not a measurement that I'm typically familiar with, right? So I want to know, I want to know how this is working, I want to know in centimeters per second. So I got to do a conversion. Okay? So things that I want to know. So it's like, all right, I will tell you that furlongs happen to be standard English units. If you're a horse racer, they're racing furlongs. And a furlong, and it's also why you have a 440 dash, by the way. Okay, you have a 440 dash because 1 furlong in units that make more sense to us is 220 yards. So for those of you that are going, what's a 440 dash? Why did I have it? Well, guess what? It's two furlongs. So that's why there's a 440 that's out there. So we've got that weird. So I've got a furlong here. And okay, fortnight. Anybody know what a fortnight is?
It's a measure of time. It's about 2 weeks, isn't it?
It's 2 weeks, 14 days. So now we've got it in units that at least we're sort of familiar with, right? So that's 14 days. And for the sake of being able to do it on my page, I'm going to go ahead and convert furlongs to centimeters, and then I'm going to convert fortnights to seconds. So I'm going to develop 2 conversion factors. So if I do a furlong, and we know that it's 220 yards per 1 furlong, and most of us know that it's 3 feet per yard. And then a lot of us know that it's 12 inches per foot. And then the one absolute exact English to metric conversion that most of us should have locked away in our heads is 2.54 centimeters per inch. So in my unit analysis, to make sure I've put them in the right place, I cancel out my units. So I get furlong per furlong, yard per yard, foot per foot, inch per inch. I'm left with centimeters. And when I plug all those numbers into my lovely calculator, I get 20,116.8 centimeters is my answer. And so if I want to keep my conversion factor, it's that per furlong. So now I've got a conversion from furlongs to centimeters. If I do my days, so if I want to do my days, and I'll just go ahead with my 14 days here. So my 14 days, we know that there are 24 hours in a day. And I know that there's 60 minutes to an hour. And I know that there's 60 seconds to a minute. And when I plug that in, I get 1,290,600 seconds. Seconds for fortnight. Okay, so there's my seconds per fortnight. So now if I want to do 594 furlongs for fortnight, I have 1 fortnight on top, divided by 1,209,600 seconds. And I have 2116.8 centimeters per furlong. My furlongs cancel, my fortnights cancel, I'm in centimeters per second, and it works out to be 9.88 centimeters per second. Kind of a fast turtle. But we were using odd units. Everybody cool? Okay. All right. In chemistry, I'm very, very persnickety about significant figures. I will tell you WebAssign, if it asks you to do something in significant figures, WebAssign gets really persnickety in significant figures. So if I have 13.842 and I want it into 3 significant figures, this is going to end up being 13.8. Now, we know the significant figures mean that this is the digit that has error in it. That's why we worry about significant figures. It's going to tell me the precision to which the measurement was occurred.
You can't see the top line.
There? So that's the precision to which the measurement has occurred. So in chemistry, it's really, really critical that you keep track of your significant figures. As we go on in engineering, it's really critical that we keep track of our significant figures. But for general physics, we're in the ballpark, and tends to be our answers tend to be around 3 significant figures. So when we're doing these, I don't focus on significant figures near as much in my physics classes as I do is when we're working on engineering numbers or we're working on a few of those things. Right now, we're learning the concepts that I don't have the same types of precision that I have to worry about as I do in chemistry. So, but just be aware of our significant figures. And typically your answers will be in 3 significant figures, unless specified otherwise. Just so you make sure that they're specified otherwise. So, a couple other things. Let's go through this a little bit. So good old trigonometry, right? We do a lot of trigonometry. Typically what you get is a triangle that looks like this. This is the X side, this is the Y side, this is the R. And we typically will see that sine of the angle is going to be Y over R. Cosine of the angle is typically going to be X over R. And tangent of the angle is going to be Y over X. All right. That's all well and good if I'm in a coordinate system that looks like that. In physics, my coordinate system might look like this. I'm going to shift it down. Might look like that. So if I've got sine and cosine memorized as X and Y, my X and Y don't look so hot right there. Right? My X and Y don't look so hot. It's a little harder for me to kind of go, okay, yeah, I could write my coordinate system that way, but that's not the way I'm familiar with it, because I'm good old, Descartes really got me in Cartesian coordinate system, and I'm kind of locked in there. So I don't like that. So what I do to kind of help myself out is I use this. This is my hypotenuse. This is my opposite, particularly when my angle is right there, and this is my adjacent. So if I look at my sine as my opposite over the hypotenuse, and I look at my x as my adjacent over the hypotenuse, and then I look at this as the opposite over the adjacent, I can turn my triangle around any which way, and I can set up my trig functions pretty easily. And I don't get myself so confused. And then we remember good old trig and good old Pythagoras. We like good old Pythagoras. So if I'm doing it in Cartesian, I get x squared plus y squared is equal to r squared. Good old Pythagoras theorem is a squared plus b squared is equal to c squared. And I can get my measurements there. And this becomes really, really important when I deal with vectors, because we are going to deal a lot with vectors. So now if I have a vector, so there's my lovely little vector. Give it a nice broad. There's my lovely little vector. So I've got my nice little vector. Things about vectors that we have to know. Vectors have direction and magnitude. If I'm looking at this point at the top, if I'm in Cartesian, that's an x, y. If I'm looking at it in polar coordinates, that's an r theta. And that's r is that part, and my angle's right there. If you use your fun little mathematics terminology, I can talk about a projection of this vector on the x-axis and my y-axis, and I can write this vector r in vector notation with an r, and this is going to be my x part with an I being my unit vector in the x direction, my y and my j being the unit vector in the j direction. And I can look at this, and this will be, as I've drawn it, it will be r cosine of my angle in the I direction plus r sine of my angle in the j direction. In the appendix of your book, you will actually see these notations again just to help remind you. The magnitude of r is going to come back in as the square root of my x squared plus y squared. And we can find our lovely angle because it's going to be the arctangent of my y over x. So we can break our vectors into components. We can break our vectors into components. And it's stuff you've been doing for a while. It's not anything totally new. And remember, with vectors, I can do vector addition graphically, and we'll do this over and over again. So I can add two vectors, and if I add two vectors, I'm adding them head to tail. So if this is my A vector and my B vector, and then I have my resulting vector, I can also do this as A, and I can have my AX in the I direction plus my AY in the J direction. And my vector B is BX in the I direction plus my BY in the J direction. I can add them together to get my R vector, and that's going to be AX plus BX in the I direction plus AY plus BY in the J direction. And then my angle, which ends up being right here, is going to go back. The tangent of the angle is just going to be my AY plus BY divided by my AX plus BX. So we can add vectors head to tail. We can add, vectors have direction and magnitude. We've talked about conversions, talked about significant figures, talked about scale. and we talked about estimates. So let's do a fun estimate. All right. So I guess it's been a while now. This one's been out there on Facebook. We have a statement. And the statement says that there are more atoms in a teaspoon of water than there are teaspoons in the Atlantic Ocean. So the question comes down to, is it true? And how would I verify it one way or the other? So, my next question is, what information am I going to need?
How many atoms are there in a teaspoon of water?
You need how many atoms are in a teaspoon of water, okay?
The size of the ocean.
Size of the ocean is the bigger one.
How many teaspoons are in the ocean?
Yeah, I need to know how many teaspoons in the ocean, but to figure out how many teaspoons are in the ocean, I gotta know how big the ocean is. Most of us could come up with. So let's talk about the size of a teaspoon. Okay. Question is, what's the volume of a teaspoon? Yeah, milliliters is easier because then I know I can go use density. Because density is water is 1 gram per milliliter. And when I know water, I know what the chemical formula for water is, right? That's 3. I've got two hydrogens and 1 oxygen, so I can figure out the atoms. But I got to know how many milliliters are in a teaspoon. Anybody happen to know how many milliliters are in a teaspoon? I do, but I even knew before I looked this one up. I went, okay, that one was easy. Huh?
10.
10? No. You're on the right order of magnitude, though.
I know how to measure it in my hand.
You know how to measure in your hand. Okay, think about that. Measure in your hand. Those of us who cook know that a teaspoon fills up about that spot. Actually, it's about 5 milliliters. Like I said, you were right order of magnitude. So 5 milliliters is the number of milliliters in a teaspoon. We can MacGyver things by doing good old MacGyver, right? He always had the right things in his pocket. I always wanted to know how he knew what he was going to need and he got the right things in his pocket. But we always know that water has a density of 1 gram per milliliter. So we have 5 grams. Uh-oh, I just lost them. So I'm going to let you guys figure it out, and Friday we will come back and see what happens.